โอเคมีคนที่อยู่ที่ OBS บ้างแล้วนะครับผมขอบอกห้อง605นะครับว่าเขาจะมีการชดเชยนะครับในคาบที่4นะครับ M605 your mathematics teacher is going to take the fourth hours. Okay, please go to please go to his classroom, online classroom after this classroom. Okay, ห้อง605นะครับโปรดไปที่ห้องเรียนของอาจารย์ณัฐพงศ์นะครับเนื่องจากว่าเขาจะขอชดเชยนะครับในวันนู่นครับในวันนี้นะครับโอเคก็สิ่งที่จะแจ้งให้คุณทราบก็จะประมาณนั้นโอเคalright โอเคนะครับปฏิหารนะครับบอกเพื่อนด้วยนะครับว่าหมดคาบนี้นะครับหมายถึง10-50เนี่ยนะครับก็ให้คุณไปเรียนวิชาคณิตศาสตร์เพราะว่าอาจารย์ณัฐพงศ์สอนคณิตศาสตร์ที่ผมเคยไปใช้เวลาเขานะครับเขาขอคืนนะครับโอเคnow it's time for us to M605. Let's continue our story. นะครับผมก็จะปล่อยคุณประมาณ10-50นะครับเนื่องจากว่าเขาเรียกว่าอะไรเนื่องจากว่าปล่อยให้คุณเบรก10 นาทีเพื่อว่าจะได้เผื่อเวลาเข้าเรียนวิชาใหม่นะครับParticle physics already. Okay, one thing that I have added is the equation of muon decay, right? This is muon minus. We're gonna have electron and is that correct? Yes. Muon minus will decay into electron, and the neutrino for the muon and the antineutrino for the electron. For the muon plus, which is the antiparticle of the muon, a typical muon, will decay into positron นะครับ605นะครับใครที่มาใหม่นะครับวันนี้หลังจากจบคาบนี้แล้วนะครับที่10-50นะครับให้คุณเตรียมไปเข้าเรียนคลาสเรียนของอาจารย์ณัฐพงศ์นะครับโอเคไหมให้คุณไปเข้าเรียนที่คลาสรูมของอาจารย์ณัฐพงศ์ที่สอนแมทผมจำไม่ได้รหัสของคุณครับที่เขาป่วยอะไรนั่นครับโอเคไหมคุณที่เขาเกิดอุบัติเหตุครับโอเคไหมโอเคplease go there. Okay, let's talk about our story. The muon plus, which is the antiparticle of the muon minus, will decay into positron. Okay, we start from the positive, and we will have the antineutrino for the muon, and here is the electron neutrino. Okay, Now we move to the law of conservation. You have seen the lepton number, right? Lepton number for electron is 1. Lepton number for positron will be -1. And the lepton number, this is the electron lepton number. And here is the muon lepton number. Electron and positron have no muon lepton number. Electron and positron have no tau lepton number, 0 here. Okay. There are 3 conservation laws in which is related to lepton numbers, because we have 3 lepton numbers, right? Electron lepton number, muon lepton number, tau lepton number, right? The electron neutrino, this one, has electron lepton number as +1. The electron antineutrino, nu bar with subscript e, will have the electron lepton number as -1. Okay, and both will have muon lepton number as 0. Both will have tau lepton number 0. Okay, what about muon? Muon with negative charge here, with negative charge, would have muon negative and muon positive, which is the anti-muon, would have 0 electron lepton number. And for the muon lepton number, it's different. Both are different. The muon will have muon lepton number as +1. The anti-muon or muon plus will have muon lepton number as -1. And the tau lepton number, both will have 0 tau lepton number. Okay. And regarding the neutrino, muon neutrino, which is denoted by nu with subscript mu, or even nu bar with subscript mu, would have 0 electron lepton number, and for muon lepton number, both are different. The typical muon lepton number would have muon lepton number as +1. The muon antineutrino, this one with bar, would have the muon lepton number as -1. The both will have 0 tau lepton number. And when we move to tau with negative is the typical tau, is the original tau lepton. Tau lepton and anti-tau would have 0 electron lepton number and 0 muon lepton number, because both have nothing to do with muon and electron. But for the tau lepton number, both are different. The typical tau lepton would have +1 tau lepton number. The anti-tau or tau plus would have -1 tau lepton number. When we talk about the tau neutrino นะครับสำหรับ 605 ที่เข้ามาใหม่นะผมจะค่อยๆชี้แจงนะครับว่าเขาให้คุณไปเข้าห้องเรียนวิชาคณิตศาสตร์ของอาจารย์รัฐพงศ์นะครับเขาจะขอชดเชยในคาบที่ 4 นะครับหลังจาก 10:50 นี้ไปนะครับโอเค and yeah the tau neutrino The tau neutrino and tau antineutrino both will have 0 electron number. Both will have 0 muon lepton number. But for the tau lepton number, both are different. The tau neutrino would have the tau lepton number as +1. And the tau antineutrino would have the tau lepton number as -1. Okay. Please note that all the neutrinos are stable, also electron. Okay. The bigger electron like muon and tau are unstable. And there are 3 conservation laws according to lepton numbers. Because we have 3 lepton numbers, there will be 3 conservation laws. The first law is law of conservation of electron lepton number. The second one is the law of the conservation of muon lepton number. The third one is the law of conservation of tau lepton number. So all of these, okay, would have their own conservation laws. Let's see what is that. The law of conservation of electron lepton number states that the sum of the electron lepton numbers before a reaction or decay must equal the sum of the electron lepton numbers after. Okay, before and after should remain the same number of electron lepton numbers. Okay, or after the reaction or the decay. The electron and the electron neutrino are assigned as a positive electron lepton number Le equal to 1. Okay, the straightforward neutrino. The anti-leptons like positron and electron antineutrino are assigned to have the electron lepton number as sorry, this is -1. Sorry for that. ผมพิมพ์ผิดนะครับ ตรงนี้ต้อง-1 นะ หมายก็ this is -1. Okay, and all particles apart from this would have electron lepton number as 0. Okay, only electron and electron neutrino would have +1 electron lepton number, and positron and electron antineutrino would have electron lepton number as -1. Okay. And for example, if you consider the neutron decay, right? Before that, we have seen neutron that decay to be okay, no. Let's say we consider beta decay. Here. Okay. This is not correct, right? It's the wrong equation. Here is correct. Neutron inside the nucleus will change itself to become proton when there are too many neutrons in that nucleus, and what we get will be electron, okay, moving from the nucleus. And we also have the electron antineutrino, this one. And here is the process of neutron decay. Okay, when the nucleus has too many neutrons, or the nucleus is neutron rich. Okay, neutron rich. So we are gonna use consider this one in beta decay. In beta decay, you will see that N is decomposed, N on neutron. It is decomposed into proton, right? This one, and electron, right? And electron antineutrino, right? This one. Let's check the electron-lepton number. If you check the electron-lepton number, I don't know which page. Here. Okay. If you go back to the table, to this figure 31, which provide the electron-lepton number, right? Neutron has 0 electron-lepton number, right? So we have 0. And proton has nothing to do with this because proton is baryon. It has 0 electron-lepton number. Okay, any particle apart from electron and electron neutrino, positron and electron antineutrino would have some value for electron-lepton number. The rest will not have electron-lepton number at all. Proton also doesn't have any value for electron-lepton number 0 here. Electron would have plus 1 electron-lepton number, so we write down here plus 1. Electron antineutrino would have negative 1 for electron-lepton number, so we write down negative 1. And you can see that the left hand side remains 0 and the right hand side will also remain 0. So we get actually the balance of this equation. We get 0 equals 0. So once we get the conservation, you could see that the total number of electron-lepton number on the left before the reaction or the decay is 0. And the total number of electron-lepton number after the decay will remain also 0. Both are equal to each other. So the electron-lepton number is conserved in this process, in this decay. So this decay could take place in nature. That's the meaning of electron-lepton number. Okay, you understand that? There will be conservation of electron-lepton number, conservation of muon lepton number, conservation of tau lepton number too. Okay, now we move to to this one. Determine which of the following decay schemes can occur on the basis of the conservation of lepton number. So, I'm not sure whether this process is correct or not. Muon decays into electron antineutrino, and muon neutrino. Is this valid? Is this correct? Is the conservation of the lepton number valid for this equation? That's the question of this example. And let's consider the second decay or the second reaction. This is pion. Okay, pion plus. Pion has 3 different types: pion 0, pion minus, and pion plus. Here is pion plus, and pion plus is decomposed into muon or anti-muon. Actually, muon plus is the anti-muon, the antiparticle for muon here. Pi plus is decomposed or decays into anti-muon, and what we have will be muon neutrino and electron antineutrino. I'm not sure whether I have written it correct. Yeah, already correct. Okay. Yeah, this one is already correct. I'm afraid that there would be typo, wrong typing in this one, but it's not. Okay, the decays in 114, okay, in both equations have something to do with electron and muon, right? The outcome are expressed in terms of electron and muon. So if you go back, there will be 3 conservation laws, right? For electron-lepton number, muon-lepton number, and tau-lepton number. Because we don't have tau-lepton at all in these 2 equations, so we are going to use only 2 conservation laws, and that are for electron-lepton number and muon-lepton number. Okay? Okay. Yes, let's consider the both electron-lepton number and muon-lepton number need to be conserved. In the first one, 114A, this one. In 114A, we consider only this equation, but for both lepton numbers, the first one is electron-lepton number and the second one is the muon-lepton number. For electron-lepton number, you could see that muon has nothing, muon here. Muon has 0 electron-lepton number, so we write down on the left 0 electron. When we talk about electron-lepton number, electron has 1 electron-lepton number, so we write down here 1. Our next particle is electron antineutrino. Because this is the antiparticle, it's going to have -1 right here. It's going to have -1 electron-lepton number, so we write down -1. The last one is muon neutrino. Because we are considering the electron-lepton number, muon neutrino has 0 electron-lepton number, so we write down 0. And let's check whether this one is correct or not. Yes, 0 on the before the decay, and after the decay we have 0 too, right? 0 as well. So it means that the electron-lepton number is conserved for this reaction or for this decay, but it's not complete. Okay, we have to also consider the muon-lepton number because the whole equation involves also muon-lepton. Okay, muon at the beginning. What is the muon-lepton number? Muon here has +1 muon-lepton number, so we write down 1 for muon. The next one is electron. Electron has 0 muon-lepton number, so we write down 0 on the right hand side. The next one is electron antineutrino. Electron antineutrino has 0 muon-lepton number, so we write down 0. And the last particle, muon neutrino. Muon neutrino is right here. Muon neutrino has +1 muon lepton number. So we write down number 1 here. And let's consider whether this equation is valid or not. Of course, before the decay we have 1, and after the decay we have 0, 0 plus 1. It turns out again to be 1. So this equation is valid. When this equation is valid, it means the muon lepton number is conserved. Okay, there is conservation of muon lepton number. Once we have considered both for this single reaction or decay, we consider both the electron lepton number and the muon lepton number. Once both are valid, we will conclude that this reaction or this decay could take place in nature. Okay, could happen in nature because there are conservations for electron lepton number and muon lepton number. Let's move to the second reaction or second decay. Pion plus decays into muon antimuon and muon antineutrino and electron neutrino. Right. Now pion. Pion is not listed in this table, in this figure, but we could easily see pion has 0 electron lepton number. Okay, if you don't believe me, you just go to the end of this chapter. Pion, where is that? Pion plus here. Pion plus has 0 electron lepton number. This is baryon number. We will talk about that later. Pion plus has 0 electron lepton number. Pion plus has 0 muon lepton number too. So for this equation, for this reaction or decay, pion plus would be 0 for both cases. Okay, 0, 0 for electron lepton number and muon lepton number. Okay, that's fair. And for the anti-muon, we could also say here, but it's no problem. Let's take a look at this table. The electron, the muon, anti-muon, this one, the antiparticle, would have 0 electron lepton number, so we write down 0. Muon neutrino, where is that? Here, would have 0 electron lepton number, so we write down here 0. And the last one, electron neutrino, this one has +1 electron lepton number, so we write down 1. Oh no, 1 here. Okay, 1. And let's see whether this equation is valid or not. You could see that there is 0 on the left, and on the right hand side we have 0, 0 plus 1, which becomes 1, right? 0 will not be equal to 1, so 0 is unequal to 1. So there is no conservation of electron lepton number to this reaction or this decay. Okay, we would simply say that this reaction or this decay would never take place in nature. Okay, and if you want to see the muon lepton numbers, we can go ahead. For pi plus, we have 0 for that, and the anti-muon, which is this one, would have -1 muon lepton number, -1, right? Muon lepton number. And second one, muon neutrino would have 1 muon lepton number, so we write down 1. And the last one is electron neutrino. Electron neutrino would have 0 muon lepton number here, so we write down 0. And let's check whether this equation is valid or not. You can see the 0 at the left hand side, and on the right hand side we have -1 +1 and 0, so it turns out to be 0. So 0 equal to 0 would be perfect, right? It would be all right. But together with the electron lepton number, the whole process here would not take place in nature, would not occur in nature, because there is no conservation for the electron lepton number. Okay, and this is the technique we could use to we could use to judge whether any reaction will take place in nature or not. Okay, ก็บทสุดท้ายจบไว้เพียงเท่านี้ก่อนนะครับนะครับให้คุณได้เข้าเรียนอันถัดไปนะครับ M605 ไม่มีการบ้านนะครับของคุณนะครับมี 604 นะครับโอ้604จะมีการบ้านเพราะเขาถึงพวกฟิวชั่นเพิ่งจบฟิวชั่นมาตามคุณมาอยู่นะครับโอเค see you on next Wednesday โอเคครับบายบายครับสวัสดีครับลืมบอกนะครับ605นะครับให้เข้าเรียนวิชาห้องเรียนชดเชยนะครับของอาจารย์ณัฐพงศ์นะครับวิชาคณิตศาสตร์นะครับเขาขอชดเชยวันนี้นะครับมีใครจะเข้าวันที่ซูมไหมไม่มีนะอันนี้ด้วยเพราะว่าปีละทัดวัดปีละทัดนี่สู race number 2 this is okay อ้าวแล้ววิพลมาก็